Hello, I am Keigo Imai. This talk is about multiparty session programming with global protocol combinators, which is a joint work with Rumyana Neykova, Nobuko Yoshida, and Shoji Yuen. The theoretical background of this work is multiparty session types. Multiparty session types, MPST, is a typing discipline for communication protocols. It ensures the absence of communication errors and deadlocks for well-typed communicating processes. The MPST programming methodology starts by writing a global protocol, which describes interactions between participants in a computation. The local behavior, also called local type, for each participant is then derived by an algorithm called projection. Finally, the programmer writes each endpoint program by following the local type. This methodology ensures protocol conformance through static type checking. If the programs are well-typed, then the programs follow the protocol. Moreover, if the global protocol is well-formed, then the communicating programs are free from deadlocks and communication mismatches. Implementing session types in practice is challenging, and the existing tools have a significant gap with the theory. Such a tool starts from the protocol description, here G, written in an external domain-specific language, DSL. And an external tool produces a set of communication APIs, here L, generated in the host language. Then the programmer writes threads, which communicate through these generated communication APIs. There are two key issues with this approach. First, the development workflow requires an external verification tool in order to write and verify the global protocol well-formedness. Second, the session type theory requires linear types as to ensure that the communication resources are used exactly once. Mainstream languages lack linear type support, and the protocol conformance through this static checking is often compromised. We present a library for programming MPST protocol that resolves these challenges. It is a library in OCaml which guarantees deadlock freedom solely by types. Our approach enables fully static verification and implementation of the whole protocol from the protocol specification to the process implementations to happen in the same language. Let me show you how to use OCaml-MPST. Open your favorite editor and let's start writing code. The code consists of two parts. 1. Writing a global protocol, and 2. Writing threads. In part 1, the programmer allocates channels which are directly generated from the protocol description written in global combinators. Global combinators are DSL for writing communication protocols in OCaml, which is evaluated to a tuple of communication channels. Then the programmer writes threads which communicate on the channels we allocated just now. Thread 1 communicates on CH1, thread 2 communicates on CH2, and so on. Then, the well-formedness of the protocol is guaranteed by the OCaml compiler. To ensure the protocol conformance, we use linearity monad, which is designed to check linear usage of channels. Hence, deadlock freedom is guaranteed statically because protocol well-formedness and protocol conformance are ensured by OCaml types. So this framework provides very lightweight deadlock freedom checking for OCaml programmers since we don't have any external tools and OCaml type checking finishes in less than 0.1 seconds. In the rest of the talk, I will tell you how we achieve deadlock freedom solely by types. See, this is rather surprising. Actually, our target language, OCaml, although OCaml has parametric polymorphism based on Hindley-Milner type inference and row polymorphism, it has no type manipulation features like type classes are implicit, unlike Haskell or Scala. Our implementation is possible thanks to two key insights, namely merging via subtyping and channel vector semantics. The first insight is that protocol well-formedness checking can be reduced to subtyping. I will demonstrate that on the OAuth Authentication Protocol. In this protocol, there are three participants: server, client, and authenticator. The server sends a login message, then the client sends its password to an authenticator. The authenticator decides whether his credentials are valid or not, and sends back the result to the server. Or alternatively, the server can decide not to authenticate the client by sending a cancel. In such case, the client notifies the authenticator that he quits the protocol. Here, we write the protocol using global combinators, our custom DSL for writing protocols in OCaml. We start with the choice at combinator, which denotes protocol branching. The arrow combinator, for example S2C login, means that the participant S sends a login label to the participant C. Note that the arrow combinator takes four arguments: the sending participant, the receiving participant, the label name, and the continuation. Now, let's see why the OCaml type checker can verify this protocol is well-formed. We break down the local behavior for participant A. There are two pieces of behaviors for A in a choice, and to verify the deadlock freedom, they need to be merged consistently. A makes a choice between password and quit. For now, we use the types from our paper to explain the merging. We encode input types and labels as variant types and tags. In the first choice branch, we have an input of variant tag password, where the square bracket denoting the variant and question mark is an input. In the alternative branch, we have a variant tag quit. The question is, what is the resulting type when merging these two variant types? Merging is crucial for well-formedness checking and ensures that protocol is deadlock-free. Our key finding is that merging of two types are justified by the subtyping, by finding the least common supertype or finding the join of two types in terms of subtyping preorder. How do we connect this key finding to OCaml? OCaml has polymorphic variants, which is grounded by low polymorphism. This enables merging of two input types into one. If the protocol is well-formed, then the protocol is deadlock-free. Now let's see what will happen if we made a mistake, for example, changing the direction of the A to C interaction. The upper part is the input of the password encoded as a variant type. The lower part is an output of quit encoded as a record type denoted by an angle bracket. These two types have no common supertype, hence these types are not mergeable. The OCaml type checker shows a type error reporting that this protocol is not well-formed. In this case, it says communication against the client are incompatible. We outlined how the OCaml type checker verifies protocol well-formedness. Now let's see how we ensure protocol conformance. The key insight here is channel vectors, which is a data structure storing pre-allocated communication channels, realizing local behavior of each participant. Channel vectors are generated from global combinators. We demonstrate this on a snippet from the Authentication Protocol we saw earlier. The arrow combinator creates binary communication channels for each communication step, channels for login, password, and result. Each end of the binary channels is stored inside a channel vector structure. Here, we have three channel vectors because we have three participants. These channels are distributed over the participants, and the order of usage of these pre-allocated channels is enforced by the structure of the channel vector. Because these pre-allocated channels are OCaml's typed channels, the type system checks the message types as well. Now we demonstrate how to program with channel vectors. First, we show the channel vector type for the client from the protocol OAuth. The angle bracket denotes the record type or the object type in OCaml with the field S matching the name of the sending participant. The inner square bracket denotes a variant type with two tags, login and cancel, matching the name of the receiving labels. Now we write the code for the client using this channel vector CHC. First, we specify the sending participant S by performing a field lookup using the hash operator. The returned value is matched against the variant tag indicating the two alternatives, login or cancel. In each case, the result is matched against a pair of the payload value and the continuation channel. Note that the variable CHC denoting the continuation shadows the previous usage of CHC, ensuring linear channel use. The next client action is sending a password which corresponds to a sending record type. Sending is done using the send primitive and two consecutive field lookups, one for receiving role A and one for the label password. In this type-directed way, we enforce protocol conformance based on idiomatic functional programming constructs like pattern matching. To enforce statically the linear usage of channels, we designed a linearity monad based on the parameterized monad by ATKey. To support pattern matching on linear values, we developed a tiny syntactic extension ppx for OCaml, here %lin. Next, we present the type-checking algorithm for global combinators. Global combinators are a set of operations applied to tuple of channel vectors. The arrow of combinator is applied to the continuation G. Here, Pi is the output and Pj is the input. First, we update the channel vector Ti for Pi to be an output type. See the bank mark denoting output. Similarly, Tj for Pj is updated to an input type. See the question mark in the resulting type. The choice combinator assumes that the participant Pa is the output. In the typing rule, the combinator leaves the channel vector type of the other participants untouched in the conclusion. The merging we have already seen is done by subsumption rule, which effectively merges behaviors via subtyping rules. Finally, the record type of the output participant P, A, is concatenated into one, preserving the all output branches. In OCaml implementation, this tuple is implemented by GADTs. The selective update of tuples are done by lenses, which is a popular technique in functional programming. Here, Pi and Pj are lenses focusing on Ti and Tj in the tuple. Merging in the choice combinator is done via low polymorphism of the polymorphic variant types, as I mentioned before. Since OCaml does not have record concatenation primitive, such concatenation should be manually written, but it can easily be semi-automated. Check the paper and the artifact for our implementation of real-world protocols, including OAuth, DNS, and SMTP. The library supports a few communication transports, HTTP, TCP, and LWT. We presented OCaml-MPST, a library for fully static verification and implementation of communication protocols. Our approach relies on a few key insights and type manipulation techniques which we believe are applicable beyond OCaml. We utilize structural typing and linearity monads to enable one to implement communication programs that are type-safe by design. The result is a static, lightweight, deadlock-free concurrency library. Thank you, and see you at the Q&A session.